All right, hello. Today I want to talk to you about types of chemical reactions, but this is a second lecture in this unit, and this lecture follows the lecture on chemical equations and how to balance chemical equations. And there is a very important reason why this lecture follows that lecture. Okay, that first lecture was trying to get you to remember what happens in a chemical change. In a chemical change, we're going to have products and reactants, or reactants and products, and what you have at the end will be different than what you had at the beginning. Remember, that's kind of the definition of a chemical change. But you also had to remember that if you have X amount of reactants, then you have to have X amount of products. Remember, the law of conservation of matter, the law of conservation of mass. You don't just lose things and you don't just gain things. Okay, so learning about chemical equations in the first lecture was all about getting you to think about chemical change, but it was also to get you to think about how those reactions are balanced. It was also to get you to think about reactants and products. Well, it's very logical that this next step would be to talk about types of chemical reactions, because here's the deal. Now you need to listen very closely. You will be able to recognize the type of reaction, okay, by the equation. You see, this is where this will all fit together. It will go hand in hand, like a hand in a glove. You will look at different chemical equations, and as soon as you look at the chemical equation before it's over with, you'll be able to identify what type of reaction it is. Now, I'm not telling you that we're trying to discuss every, we just want to talk in this particular lecture. We want to talk about 5 different types of chemical reactions. Well, what are the 5 types that we want to talk about? Well, I'll tell you what let's do. Let's name them. Then let's get a working definition of each of them, and then let's close by being really a lot more precise to actual atoms and compounds in real life that might, undergo this type of reaction, okay? But remember, before we even get started, okay, see the big picture. If you can understand chemical equations and how to balance them, then before it's over with, you'll be able to identify the type of reaction from the equation. Reaction number 1, combination. Okay, combination reaction. Reaction number 2, decomposition. Ultimately, this one will probably be intuitively easy for you because nearly everyone has seen something that is dead or has died or is decaying, so this idea of breaking down I don't think is really foreign to us. Okay, so decomposition probably, that concept's going to be pretty easy to you. Single replacement, double replacement, and combustion. These are the 5 types of reactions that we are going to explore in the next 15 to 20 minutes. So what are we going to do? We're going to learn their name, we're going to learn a little bit about them, and then we're going to look at actual chemical equations, balanced chemical equations that illustrate this type of reaction. So let's begin with a visual aid, all right? This is not accurate to atoms or compounds. I mean, we don't have any element A's and element B's and compound CB's or whatever. But what we can do here is we can use this slide to sort of look at the big picture. What happens overall in each of these reactions, okay? Now you'll notice, however, that on this particular slide, I only have 4 of them, and you said we were going to talk about 5. The reason why, I'm going to tell you right now, synthesis and combustion, okay? Synthesis and combustion are in many ways the same, except, obviously, if something combusts, it burns, and it gives off heat, and it gives off light. Well, you can have a synthesis reaction that isn't combustion. So there is some difference, obviously, between the two, even though the result is pretty much very, very similar. So we'll make sure you understand that before we're done. But understand, that's why there's only 4 on here. So here we go. Open up your eyes and your minds and let's think. And right now, our job is not to identify them by name. It's to identify them by what happens overall. Big picture. What happens overall? So here we go. If I have A plus B and that yields or gives me AB, then I can tell that that has to be a synthesis, because synthesis in this case means to put together. So I went from a couple of reactants, right, to one product. So obviously I had a synthesis reaction, or I had a combination, okay? They are combining, all right? Now, as I said, and I'll kind of continue to plant little seeds, this would also be similar to a combustion reaction, except remember that if a combustion reaction is when something burns, that's definitely, I think, a noteworthy type of reaction. So while they are similar, okay, they'll also be a little bit different. But because they are so similar, I'm not going to list a fifth one. Number 2, I have AB. Now, all of a sudden, what do I have? I have A plus B. Well, what has happened? And you're like intuitively, mentally, visually, you can see that obviously A and B came apart. That would be a decomposition, okay, coming apart. I would have one reactant, but now I have two products, right? Okay. All right, what about A plus BC? Well, what do I end up getting? I get AC plus B. Well, don't overcomplicate it all. You can simply tell that A has taken B's place, and now B has been liberated, so to speak, and it is by itself. So this is what we call a single replacement or a single displacement. And what happens when you get displaced? You get knocked out of your seat, right? Okay, so we have a single replacement or a single displacement. All right, what about a double? Well, I think you're probably already a step ahead of me, because you're like, oh, well, I mean, if this is a single, then a double is just going to be two items, right? Well, in this case, it's also noteworthy because those two items that are displacing or replacing one another, okay? So we have AB plus CD. Now, I would have done this, I honestly would have done this a little bit differently, quite frankly. And I would have written CB plus AD, okay? I would have kept kind of the same. But what I really want you to see, the most important thing to me at this point, is that you can see that A and C have swapped places, all right? So what have we here? We have a double displacement or a double replacement. And let's not overcomplicate that, okay? Now, I do want to tell you that in each one of these reaction types, okay, the conditions have to be right, and sometimes there are other factors that come in. These reactions don't necessarily just occur. I mean, I don't think we want to make the assumption that we mix two things together and we just always get a reaction. But sometimes we do get certain reactions. And so here are, 4 items that we could possibly get. Okay, synthesis is a combined. Decomposition, coming apart. Single replacement, we have a single replacement. Double displacement, we have a double displacement or double replacement. So, and combustion, once again, falls into the combination category. So we have 5 types by name. We have 5 concepts, okay? All right, now let's get 5 definitions. And you may say, well, haven't we already done that? Well, maybe we have, but let's put a little wording to this, and we'll give it to you also in your notes that you can study and look over. And then we'll close by looking at some actual chemical equations. And that's why we learned about chemical equations first. Here we go. So what is a combination reaction? Well, by words, a chemical change in which 2 or more substances react to form a single new substance. Okay? Take your mental picture. A plus B gives you AB. Okay? What is a decomposition reaction? It is a chemical change. We keep harping on that. Chemical change, chemical change. You're getting something different, remember? A chemical change in which a single compound breaks into 2 or more simpler products. Well, what do we have here? We have a compound breaking into 2 or more simpler products. Let's keep it simple, okay? Number 3, what is a single replacement reaction? It is a chemical change, remember, chemical change, in which one element replaces a second element in a compound. So what did we have here? We had this element replacing this one, okay? Let's not overcomplicate. That's a single replacement or a single displacement. What is a double replacement reaction? Once again, it is a chemical change in which there is an exchange of positive ions between two compounds, and it's also called a double displacement. I want to remind you of something. I want to remind you of when we talked about ionic compounds in our first trimester, and we always listed the positive cation, and then we would list the negative anion, right? Well, so what are they telling you here? They're telling you that when these two swap places, they're telling you that these are the cations, and they are simply swapping places. So what are they, or what is it? It's a double replacement or a double displacement. Okay? All right, so here we have the list, here we have the concept, here we have the definitions, okay? Now, let's go to the real meat, which is, let's look at the actual equations. Okay, let's put this to work real life. So you'll notice that the first one, remember, was a combination reaction, okay, or synthesis on our previous slide. Well, what did I do? I listed two of them. Well, why in the world did you list two of them? Because you don't list two of them here. You don't list two of them here. So why did you list two of them here? Well, what did I tell you earlier? I told you that combustion also fits into this overall concept. Okay, when we burnt the magnesium strip in class, it joined with oxygen. So magnesium and oxygen combined to produce magnesium oxide. Now, obviously, that gave off a brilliant light. It gave off smoke. You know, if you have a combustion reaction, you're probably going to give off heat. So obviously, even though it may be a combination, it's noteworthy because it's a very noteworthy reaction. All right, but potassium and chlorine will combine to produce potassium chloride. Now, this is where you go back in your memory banks, because when I taught you about ionic compounds previously, we talked about salt. We talked about what we called light salt. We talked about people with high blood pressure. We talked about how potassium and chlorine would also make a crystalline solid. You know, you remember talking about characteristics of ionic bonds. Well, in the process of making light salt, okay, or mixing some potassium chloride in with sodium chloride, we never once said you were burning it. Okay, so this is not a combustion. It's not a combustion, but it certainly is a combination. And you can see that with your eyes. That's very, very, just common sense. It's very intuitive. You can see that these two items have joined together. So a combination reaction doesn't have to be a combustion, okay, but it could be a combustion. So that's how the two of them go hand in hand, because at the end of the day, they're both combination reactions, okay? So is this equation balanced? Yes. What happened? Well, in this case, magnesium and oxygen combined, or in this case, potassium and chlorine combined. All right, moving on. In a combination reaction, we had two or more, but we only ended up with one. That's why it's called combination. All right, decomposition reaction. Well, in this case, we'll only look at one. We'll look at mercury oxide. Now, here's the question you might ask. What made it decompose? And I'll just be honest with you, I don't know, okay? In this particular example, I don't know, there's usually a causative agent that causes something to decompose. Like, for instance, light. That's why a lot of medicines are stored in dark bottles, because light will literally cause some of those compounds to decompose. Well, you certainly wouldn't want that, okay? You wouldn't want that to happen, so you store them in brown bottles. Heat could be something else that might cause something to decompose. In this case, I don't know why. We're just considering that it did decompose. So, by definition, by concept, if you decompose, you will break into, obviously, two or more parts. Okay? So, is it balanced? Yes. And remember, we know how to make things balanced by using coefficients and making sure that we have the same number of atoms on both sides to meet the law of conservation of matter, okay? But we really want to know in this discussion today what happened. Well, what happened is that mercury oxide broke down into mercury and oxygen. So that would be, by definition, a decomposition reaction. Now, at any point in time, you know, you have my permission to hit the pause button. You have my permission to rewind. You have my permission to watch something more than one time. You do what you have to do to digest the material. Okay? All right, number 3. We're already ready for a third reaction type. What about a single replacement? Well, here I have a potassium that is interacting with water. I mean, you can see that from the reactant side. Well, what ends up happening? Well, what ends up happening is you end up with something called potassium hydroxide. Why? Well, I think if you'll look at this and you'll try to look with me and think with me, you will say, well, Mr. Day, it looks like a K replaced an H. Okay? I mean, if you look at this and you look at how it's balanced and you look at your reactants and you look at your products, then you can see that we had a single replacement. We had a potassium, which ended up replacing a hydrogen. So, but it was only one replacement and one single replacement. So that is a single replacement item, okay? So what do you get? You get a situation where one element replaces another. Now, in these reactions, you might have a gas created, you might have some heat, I don't know. There are items that would be produced in some of these reactions that we're probably not talking about. Okay, what we're talking about really is just overall what happened within that reaction type. Well, within this reaction type, we had a single replacement. So now we're already ready for the fourth one. But before we talk about the fourth one, let's make sure we understand something, okay? Just because you mix two things together doesn't mean you're going to have a reaction. Okay, now think about this, please. Atoms don't just like wake up one morning and they're not cognizant items with souls who say, oh, I think I'll do this today, okay? All right, so what does govern some of these reactions? What does govern them? Well, honestly, instead of memorizing a bunch of stuff, we give you tables like this table right here, which is an activity series of metals. So this is a chart. Now look, because it's plain, it's easy to read. It says decreasing activity. So as you go down the activity series here, you have decreasing, it decreases. Now you're like, well, what does that really mean? Well, here's what it means very simply. If you're down here, you're not going to replace one of these guys up here, okay? But if you're up here, you could very easily displace one of these guys, okay? You could knock them out. You could take their place. So especially when we talk about replacement or displacement reactions, okay, number one, you're going to learn how to recognize it just by looking at the equation. So if I give you an equation where it's an actual displacement or replacement reaction, you'll just know because you'll be able to recognize it. But what if I gave you an equation and I said, will this happen? You know, would they replace one another? Well, then you would simply look at something like this to help you know whether they would or wouldn't, because atoms don't just do stuff at random, okay? So we will use this more as we go and as we practice together. All right, so here we go. We're already ready for number 4. And honestly, then we're done because we don't really need to mention number 5. Why? Because you already know that a combustion reaction, we've combined. A combustion reaction is a combination reaction. So we're on our last reaction type, which is what? Which is a double replacement. So in a double replacement, and I have to kind of chuckle when I look at this one because we would never do this in class. That's sodium cyanide, which is a poison, and sulfuric acid, which would be, you know, it could be a fairly concentrated acid. So I have to chuckle on this one, but it doesn't matter. Let's just look at what happened in the equation. Well, it's pretty simple when we look at it. When we look at our reactants and when we look at our products, we can see that sodium and hydrogen have swapped places, okay? I mean, let's not overcomplicate. We can see it. We can see it from the equation. They have swapped places. We have cations that have swapped places. So what is that? Well, we know that if we have this double swap, that's what's known as a double replacement. Okay, but here's an actual equation that shows you, okay, an example. All right? And so we have a double exchange of positive ions. Okay? So let's recap very quickly. Okay, very quickly. So what's the purpose of this lecture? Understand the purpose. It's for you to identify the 5 types of chemical reactions by name. So you're going to identify them by name. You're going to identify them by concept, just overall what happens. And then last but not least, you're going to actually be able to recognize them by looking at the actual chemical equation and saying, oh, well, I can tell what that is. That's a such and such reaction. All right, go over your notes, look over it, listen to the lecture, do the lecture assessment, but remember to look at the big picture and what the 3 goals are.